So let's look at question 1 of assignment 2, where we are asked at inversion what the surface potential of an NMOS transistor is. Now inversion is defined as the point at which the channel is as n-type as the body is p-type. So therefore at inversion the channel carrier concentration is Na, and since the bulk is p body and so electrons are minority carriers, the concentration is the intrinsic concentration squared by Na. Now by the law of mass action, since psi s is assumed to be the potential difference between the two regions, we get that Na divided by Na is equal to e power psi s by kT by q, right? And rearranging this expression, you will get Na by Ni ln 2 kT by q, or let's keep the 2 inside, is equal to psi s, which is the surface potential. And bringing that 2 outside of the logarithm, you get this expression. So in the second question, we are given for an NMOS transistor, VSB is equal to 0.8 volt and VTH naught is 0.4 volt, and the VG is at 1.8, but since the VS is also at 0.8, we have VGS is equal to 1 volt and VD is at 1 volt, which means the VDS is equal to 0.8 volt, 1 minus 0.2 volt. So looking like it clearly indicates that it's operating in the linear region because the VDS is very small. But let's work it out and see what happens. Initially, let's look at what the VTHN is going to be, which is VTN plus gamma type times square root of mod psi s plus VSB minus square root of mod psi s. Substituting the values of 0.4 plus 0.4 times square root of psi s is 0.6, 0.6 plus VSB is 0.8 minus square root of psi s is 0.6. Doing this, you will find that the answer is, let's see, so this is 0.4 plus 0.4 times 0.408. So this is equal to 563.4 millivolt. So that's the answer there. So this is the threshold voltage required. So let's look at question 3. We are given a gate capacitor with W and L as such and 0.4 nanometer gate oxide thickness, and we provided the relative permittivity of silicon with respect to vacuum permittivity. So this is a case of a parallel plate capacitor with the following parameters. So the capacitance is simply epsilon naught epsilon r into the plate area divided by the distance between plates. This is now simply 3.9 into epsilon naught into the plate area is W into L, so that's 0.6 micro into 0.18 micro divided by the thickness, which is 0.4 nano. Doing this, of course, you will find that the capacitance in femtofarad is within that range. So this is the question where we are given the drain and gate and body voltages and asked to find out what the drain diffusion capacitance is. we basically have to assume that the drain to body diode, sorry, the drain is an NMOS transistor, it's an N plus drain. So it's essentially a drain to body diode that's in reverse bias, right? Because the body is grounded, right? And we just have to find the drain diffusion capacitance. So the formula is fairly straightforward. Cj drain is equal to Cj bottom plus Cj sidewall, and of course Cj bottom is equal to Cj naught bottom, which is the value for zero reverse bias, divided by 1 plus V reverse bias divided by psi naught, the whole power m, which is the ideality factor. And of course this is for the bottom, because we've given one for the bottom and one for the sidewall. So we'd have to calculate the sidewall with the formula Cj sidewall similarly as Cj naught sidewall divided by 1 plus V bias by VB should not be confused as V body, it's VSB divided by psi naught. Sorry, V drain to body, it's the drain to body diode, so the reverse bias is VDB, and this is divided by MJ sidewall. This is MJ, or the bottom junction, should be MJB, but okay. So yeah, these, and of course Cj naught bottom is equal to the bottom capacitance per unit area times the W into L, right? And that is Cj, the given value Cj into W into L, which are given here, and of course Cj naught sidewall is equal to the per unit length capacitance CJSW times the length or the perimeter of the sidewall. Now the sidewall has the following dimensions. This is the channel, so we ignore that side, and this is the width of the transistor. So it has W plus 2L as its perimeter, ignoring the channel, so it is W plus 2. Of course, now if you punch in all the values given in the question in all these formulae, you will find that the capacitance in femtofarad lies in this range. So question 5 is almost exactly the same as question 4. It's the same template as question 4. It's just that now the drain is grounded along with the substrate, so VDB will be equal to 0. So you don't need any of these. You'll just be that Cj naught bottom and Cj naught sidewall will be Cj bottom and Cj sidewall respectively, and the junction capacitance is the sum of those two. And the only thing to note really here is that the value is higher. That is, the more you reverse bias it, the smaller is the capacitance. In here there is no reverse bias and you have a large capacitance. So for questions 6 to 10, we are given the following common data, parameters regarding NMOS and Pmos, and we are asked to find the drain current ID under various conditions. To be noted, we are not going to specify a direction really. So if you had plus or minus this answer, you will be awarded marks accordingly. So IDS or IDSD, it doesn't matter that whatever direction you've taken, you will be given the correct answer as long as your magnitude is correct. So questions were solved with magnitude of drain current in mind. So the only thing that's left is to remark upon the Pmos transistor universal current equation. So what you would get is ID, which is for a Pmos, if current is flowing like that, this is the drain and this is the source, and the drain current is defined as going into the drain, right? So ID has the formula K prime P, which is negative, into WP by L P into VGS minus VTP. VTP is also negative, minus Vmin by 2 times Vmin times 1 plus lambda P VDS. Lambda P is negative, and of course VDS would be negative for a Pmos in general. So Vmin, and Vmin of course is the max. So it's for a Pmos, it's max of VGS minus VTP times VDS, comma VDS, and VD sat P, which is also negative. So the one with the least magnitude, or because it's negative, the one which is the max of these three would be Vmin. So much like an assignment 1, all you need to do is find Vmin, and if it comes out as this, it's saturation. If it comes out as this, it's linear, and if it comes out as this, it's velocity saturation. And if it's a short channel transistor, you would have to include the channel length parameter. If it's a long channel transistor, then lambda p equal to 0 for long channel, right? And yeah, so if you had solved it with the drain current as shown here and gotten the value that's negative of all these answers, then you will be given marks for that. So plugging these into question 6, 7, 8 and 9, you get the following values. Right, of course this current is only for when VGS or mod VGS is greater than mod VTP. Of course, mod VGS itself has to be less than 0. The 10th question is just an expanded version of questions 6 to 9, where you've not just been asked to find the drain current, but also the threshold voltage. The threshold voltage formula, of course, is VTP is equal to VTH naught P, which is negative, plus gamma P, which is also negative for a PMOS, times mod of psi S, which is negative, plus VSB, which since the source is at VDD will be positive, plus square root of mod psi S. Right, so just substituting the various values into this will give you this answer, and getting that VTP into the universal current formula will give you this answer. And of course the VD sat P is such that the VDS and also the VDS is such that the transistor will come out to be in velocity saturation. Yeah, so in question number 11, we are given that the body is tied to VDD plus 0.1 volt and the source is tied to VDD. What happens to the threshold voltage and the source to drain current? So in this question, we can analyze this question straightforwardly from the threshold voltage equation. So as compared to the case, so in this case VSB is minus 0.1 because VS is VDD and VB is VDD plus 0.1. So that VDD cancels and it's just minus 0.1 volts. So yeah, in this case, this is how the equation comes out. and comparing it to the case where there is no VSB, that is VSB is equal to 0. When VSB is 0, it's mod size in both the square roots, so they subtract to get 0. So it will be 0, this term will be 0. But when it's minus 0.1 volts, since psi s is negative, you're adding two negative numbers, it's becoming more negative. That means the magnitude is increasing. So this whole thing becomes some positive delta, right? Because this is now greater than this, right? So this whole thing is some positive delta. And since gamma is negative, of course, this now becomes some minus. So this whole thing becomes some minus delta, right? And of course, so this whole thing is now some negative number, so VTH naught is negative. You're adding two negative numbers, it's becoming even more negative. So therefore, the answer is VTH naught decreases, but actually mod VTH increases. So this is wrong, and this is correct. Now, if VTH decreases for a Pmos, the source to drain current decreases. So this is correct, and this is wrong. So the 12th question, it's about gate overlap capacitance. The correct answer is that the gate overlap capacitance is proportional to the width and independent of the channel length, because no matter how long the channel is, the overlap is only on the edges. But of course, if it's very wide, then a longer section will overlap, and so it's therefore proportional to width and independent of channel length. So in the 13th question, we are given that Vs is greater than Vb. That is, we are in the source to body diode is reverse biased. And so now we have junction capacitance over there, and we just need to know how it varies with increasing source voltage, right? So the capacitance formula is Cj divided by 1 plus Vsp by phi naught the power m, where now if Vsb increases, right? Increasing source voltage means Vsp increases. Then the denominator, it increases, right? So therefore the capacitance overall decreases. So the answer is decreases with increasing source. So we are given the subthreshold leakage at 0 volt VGS and are asked to find what it is at minus 0.1 volt VGS, right? So let's say ID1 is the drain subthreshold leakage at VGS1 and ID2 corresponds to that of VGS2. Then of course we get ID1 by ID2. It's not hard to see that this is exponential of VGS1 minus VGS2 by n phi t from this formula, right? So simply taking ID1 as 150 nanoamps, VGS1 as 0, and VGS2 as minus 0.1 volt, and as 1.5 and phi t as 26 millivolt as stated in the problem, you will get that the answer is 11.5 for ID2. So in the 15th question, we are asked what the lowest value of VGS will ensure the least leakage current. It's the point at which gate induced drain leakage will set in. So if you were to reduce the VGS below the point of Gödel, actually the leakage current will increase because of the Gödel phenomenon. So in the 16th question, we are asked the threshold voltage of an NMOS transistor doesn't change when VDS is 0.1 to VDS is VDD. This is quite a large change in VDS, but the threshold voltage of the NMOS doesn't change. This means that the Dibble coefficient alpha Dibble, which is equal to VDS2 minus VDS1, VTH2 minus VTH1, where VTH2 corresponds to the threshold voltage is VDS2, and similarly for VTH1 and VDS1. This the numerator is now 0. This is equal to 0. This is the answer.